When designers are building models, they base their designs on full-size structures. Take this Olympic pool, for example. This pool is a rectangle with a very specific size. The lanes are at least 50 meters long, and the pool is at least 25 meters wide. Each lane must be 2.5 meters wide, and there are 8 usable lanes. Now, if I were to create a pool with a similar shape, I would use a single scale factor to determine the widths and lengths. Since the scale factor is a similarity transformation, the shapes are similar. See? Here, the scale factor for the width is 25 meters per unit, and the scale factor for the length is 50 meters per 2 units, which simplifies to 25 meters per unit. The sides have the same similarity transformation, and they're both rectangles, so the pool is similar to the model. Now, if designers only had one factor to consider, that would be all there is to it. But there are many other factors that come into play, especially when it comes to building and maintaining a pool. Take, for example, the length of the lane markers. They scale the same as the side lengths, but the evaporation from the water surface scales the same as the surface area in the model. Hey, Tony.
Oh, hey, Enid.
This is perfect. We were just talking about scale models.
Ah, well, that's lucky, because I just so happen to have 2 models to help demonstrate.
Yeah, I see you have 2 cubes, one with a side of 1 square and one with a side of 4 squares.
And the smaller cube is a scale model of the larger one.
And that's great, because it adds to the different types of scale factors we can visualize. We already know that some things, like the lane markers, scale with the side lengths.
And some things, like evaporation, scale with the surface area of the water.
That would be like the top of your cube.
Right. But what about the sides of the pool, like if we were going to paint it? That would be like the sides of the cube. So it would scale with the surface area of the cube minus the top.
Or if you wanted to balance the chemicals added to the pool, you would have to know how much water the pool holds.
And that would scale with the volume.
So let's take a quick look at the 3 different scale factors. First, let's just look at the top square. The perimeter of the smaller model is 4 units.
And the perimeter of the larger square is 8 units.
Yes.
6, 7,
So
8.
that gives us a scale factor of 4/8, which simplifies to 1/2. So that's the same scale as a single side.
But now let's look at the area of both models. The smaller model has an area of 1 square.
And the larger cube has an area of 4 squares. So that gives us a scale factor of 1/4, which is different from the perimeter.
So the surface area scales in the same way. The smaller model has 6 squares on the surface.
And the larger model has 24 squares on its surface. So that gives us a scale factor of 6/24, which simplifies to 1/4 again.
Ah, but what if we take the top away, like if we were going to paint the pool?
Then the smaller model has 5 squares, and the larger model has 20 squares, so that still simplifies to 1/4.
Now let's consider the volume. It gives us one more scale factor. The small model contains 1 single cube.
And the larger model has 8 cubes. That's 1, 2, 3, 4, 5, 6, 7, 8.
So the scale factor of the volume is 1/8.
So the model's useful, as long as you know the scale factor for each situation.
And as long as you know what you're scaling, like the perimeter, the area, or the volume.
Which helps a lot, except for one thing.
What's that?
I don't think I could fit into this little thing, and I really want to go swimming.
It gives me an idea. I'll be right back.
Yeah.
Woo! Enid, come on in. The water's perfect.
I'm gonna go in.
Where are you going?
I have to go change!